So now I'm going to show you a couple of cool things about these two results. So we had ln of 1 plus x equals the sum from n equals 1 to infinity, negative 1 to the n, x to the n over n, and inverse tangent x equals sum from n equals 1 to infinity, negative 1 to the n, x to the 2n minus 1 over 2n minus 1. And I recapped those because I had this one wrong. If you noticed, maybe you did, when I presented it over here, I left off the negative 1 to the n. So there's supposed to be a negative 1 to the n right there because we can see that this series alternates, so it needs a negative 1 to the n. All right, so with that correction, here is this series, and here's the first one that's sort of super cool. All right, so first of all, the interval of convergence for all of these is negative 1 to 1. They converge on negative 1 to 1. All right, but and that's not including the endpoints, right? Because for a geometric series, if the r equals negative 1 or 1, the series does not converge. But with this n here, this is no longer a geometric series, right? The original series that we looked at was geometric. So if x equals 1, this clearly does not converge because I'm just going to have 1 plus 1 plus 1 and we're adding it forever, right? But this one, because the denominators now, what happens if x equals 1? If x equals 1, then what I have is the sum from n equals 1 to infinity of negative 1 to the n times 1 to the n over n, which is just 1 over n. All right, but that converges because it's the alternating harmonic series. Converges because it's the alternating harmonic series. You can also say it converges by the alternating series test. This is an alternating series. It's a decreasing, the 1 over n is decreasing, and the limit as n approaches infinity of 1 over n is 0. So this series converges by the alternating series test. So even though it's outside the domain of convergence of the original series, this series converges at one more point than the original series did. And that point at which it converges is very cool because it gives you the harmonic series, but look what happens when you put the x equals 1 over here. It gives you ln of 2. And that's another justification for why the sum of the alternating harmonic series is ln of 2. We saw that in demonstrated geometrically in a note that I attached to one of our earlier lectures. So that's a pretty amazing fact. Alternating harmonic series not only converges, it converges to the ln of 2, and we can prove that by having integrated 1 over 1 plus x. So we took that geometric series, we did a substitution, we did an integration, we ended up with this cool fact. And that's what manipulating these series is all about. Now, let's look at this one where we're saying that this series converges to inverse tangent of x. So I thought I'd sort of show, look at what does it mean that this series converges to inverse tangent of x. So I chose a number that was solidly within the interval of convergence, which is negative 1 to 1. And I chose, what if x equals 0.5? All right, then according to this equation, the sum from n equals 1 to infinity of negative 1 to the n of x to the of 0.5 to the 2n minus 1 over 2n minus 1 should be exactly equal to the inverse tangent of 0.5. So what I did was I set that up as a table on my calculator here. So what I did was I set y1 is the sum. I had to use the alpha key to get n equals 1. I wasn't sure this would work, but it does. So, and because x is my variable, so the x is the variable that I want to be increasing over time. All right, so this was y as a function of x, but the x is up here. So what this is going to do is give me x partial sums. So this is the sum from, when x equals 1, it's going to be sum from 1 to 1. When x equals 2 is 1 to 2, 1 to 3, etc. And the way I set the table up, that x, which is really the partial sum that I'm taking, is starting at 1 and it's increasing by 1 every time. All right, so then if we look at what that is, I put in the function negative 1 to the n minus 1. Oh, I put n minus 1 this time? That's interesting. There's an n or n minus 1. The first term is positive. Therefore, if I do negative 1 to the n, when I have n equals 1, I would have a negative. So this is n minus 1, not n, not just n. The exponent is n minus 1. All right, well, I had it wrong there, but I have it right here. And then I just set up just like what I have here, 0.5 to the 2n minus 1 over 2n minus 1. All right, and then down here, just for comparison, I set up inverse tangent of 0.5, which is what we're comparing it to. So now, if you do the table, these are the partial sums. This is the first partial sum, second partial sum, third partial sum, fourth partial sum of this infinite series. And this is the calculator's value for the inverse tangent of 0.5. And you can see that they converge very quickly. And by the time you get to n equals 7, you have 5 decimal places of accuracy. So then what else I did was I said, well, let's pop out of that and let's see how many partial sums it takes me to get within 10 decimal places. So here's your calculator's inverse tangent of 0.5 to 10 decimal places. I only had to go to n equals 13. The 13th partial sum gave me a match to 10 decimal places for the inverse tangent of 0.5. And I'll show you a couple other cool things you can do with that in the next vid.